In this segment, we'll introduce and discuss the important concept of compactness. We'll start by discussing collections of sets, then open covers and subcovers, and we'll use this to define compact sets. And the main result we want to prove is that the n-dimensional cube in Rn is a compact set. First, a quick reminder of De Morgan's laws, which state the following. Suppose you have some collection of sets E alpha indexed by alpha. The complement of the union of these sets equals the intersection of the complements, and the complement of the intersection of these sets equals the union of the complements. And these are extremely useful in taking a claim about open sets and converting it into a claim about closed sets, because we know that a set is open if and only if its complement is closed. So let's consider some such statements. For any collection of open sets, the union of these sets is open. Now this follows directly from the definition of open sets. Every point in an open set has to be an interior point, and so therefore it must be an interior point also of the union. Now you can take this statement and use De Morgan's laws to show that for any collection of closed sets, the intersection of these sets is closed. Furthermore, you should verify that for any finite collection of open sets, their intersection is open, and for any finite collection of closed sets, their union is closed. Now this does not apply for infinite sets. You should be able to find an infinite collection of open sets that are not open. And you can do this using open intervals in the set of real numbers, such that the intersection is a singleton set, which is obviously closed. And you can use that example to construct an example of an infinite collection of closed sets using De Morgan's laws, such that the union of this infinite collection of closed sets is not itself closed. Next, we define open covers and subcovers. Given a set S in a metric space X, an open cover of S is a collection of open subsets of X such that S is contained in their union. And if we have an open cover G alpha, any subset of this collection of sets that's also an open cover of S is called a subcover. And we'll use this to define compact sets. We say that a set S in a metric space X is compact if every open cover of S has a finite subcover. And this must be true for every open cover of S, not just for some open cover. Let's look at a couple of examples. First, note that all finite sets are compact in any metric space. Now to see this, let S be any finite set, and let G alpha be an open cover for S. Now each element of S must be contained in at least one set in this collection, and since we have a finite number of elements of S, we can take one open set in the collection for each of these elements, and the set itself will be contained in their union, which is of course a finite collection of sets. Now you should be able to show that the set of real numbers is not compact, and you can do this by taking a collection of intervals that is a cover for R, such that no finite subset of this collection is itself a cover for R. And you can use exactly the same approach to show that the open interval 0, 1 is not compact in R. And I leave that as an exercise. Now the main result we want to prove is the following. The n-dimensional cube is a compact subset of Rn. And we're going to prove this by first considering n is equal to 1, and we'll consider the interval 0, 1. So a equals 0, b equals 1. And then we'll argue that the basic idea of the proof generalizes to arbitrary n. So let's start by trying to prove that the closed interval 0, 1 is compact in R. So let's assume that the closed interval is not compact, and we'll obtain a contradiction. So if it's not compact, then there must exist an open cover with no finite subcover. Let's call this open cover G alpha. Now since G alpha has no finite subcover, if we bisect this interval and consider the intervals 0, 1/2 and 1/2, 1, at least one of these is not covered by any finite subset of G alpha. If both of these were covered by finite subsets of G alpha, then we could take the union and get a finite subcover for 0, 1, and we're assuming that it has no finite subcover. Let A1, B1 denote the interval that is not covered. It's going to be either the left interval or the right interval. Now applying the same reasoning, we can bisect this interval into a left interval and a right interval, and at least one of these is not covered by a finite subset of G alpha. If they were both covered by finite subsets of G alpha, then A1, B1 would be covered, and by hypothesis, it is not covered by any finite subset of G alpha. Now let A2, B2 denote the interval that is not covered. It will be either the left interval or the right interval. And we can iterate this reasoning to get a sequence of nested intervals. So you can see where we're going with this. We'll obtain a sequence of intervals, each of which contains its successor. And these are intervals of decreasing length, in fact, in the limit of vanishing length, such that no interval in this collection is covered by any finite subset of G alpha. Now we'll apply Cantor's nested interval lemma, which states that the intersection of these intervals must be non-empty. In fact, it must have length 0, so there exists some real number c in R such that the intersection of these intervals is equal to the singleton set that contains c. Now, since G alpha is an open cover for the unit interval, there must exist at least one set S in this collection that covers C. And furthermore, since S is open, C must be an interior point of S. Now, since C is an interior point of S, there must exist an epsilon neighborhood of C that is contained in S. And you should convince yourself that this implies that for n sufficiently large, there must exist an interval in this collection of nested intervals such that the interval a n bn is contained in S. But now we have a contradiction, because if a n bn is covered by S, then a n bn has a finite subcover, and we constructed this sequence of intervals to ensure that none of them is covered by any finite subset of G alpha. So we've proved the result for n is equal to 1. You can see that there's nothing special about the unit interval in our reasoning. So we've proved this for any closed interval in R. And the question is whether we can generalize this reasoning to apply to any arbitrary n. So first consider n is equal to 2. So in that case, we have a square in R2, and we want to show that it's compact. Again, we can do it by contradiction. So suppose it's not compact, and suppose G alpha is an open cover for this square. Well, we can bisect this square vertically and horizontally to obtain 4 identical smaller squares such that at least one of these 4 is not covered by a finite subset of G alpha. And then we can proceed exactly as we did before to get a sequence of nested squares instead of intervals, such that the intersection of these sets is a singleton set C. And then we apply exactly the same reasoning as before. C must be contained in some set S. It must be an interior point of S since S is open. And so therefore, for n sufficiently large, one of the squares in our collection must be fully contained in S, and so therefore has a finite subcover. And you should be able to see that this reasoning generalizes not just to n equals 2, but for arbitrary n. Now we'll use this result in the next segment to show that a subset of Rn is compact if and only if it's closed and bounded. And that's a very useful property, because it's much easier to verify that a set is closed and bounded than it is to directly verify that it's compact. And that's it for this segment.